Let's get started. So, hi everybody, welcome to another SNAPP lecture. So today we're delighted to have Hamsa Bastani. Hamsa is an associate professor in the Operations, Information, and Decisions uh, department, as well as Statistics and Data Science at Wharton at the UPenn. And Hamsa's done lots of amazing work, both on the methodological side and with lots of direct impact. She's won numerous awards for her work, including the Wagner Prize, the Pierre Scala Award, and the Nicholson Prize. And today we're delighted to have Hamsa talking about the winner's curse in data-driven decision making. So please, Hamsa, take it away.
Thanks so much, Ziv. And it's great to be here. I was naive enough to not know about this series until I got invited. And now that I'm looking back, I'm like, what have I been missing out on? So I'll be talking today a little bit about the winner's curse. This is actually a well-known phenomenon. So I'm going to review a little bit what it is first. And then I'm going to kind of try to illustrate that it's sort of a pervasive issue in our field in particular, that we don't account for it in data-driven decision making. And that can lead to kind of erroneous conclusions, and then how we can try to sort of mitigate this. I'd love to keep it as conversational as possible, so please ask questions, unmute yourself. I definitely don't have enough slides for an hour, so please chime in. This is joint work with Bryce McLaughlin, who is my postdoc and who is now joining BC, and Osbert Bistani, who works both as my co-author and my husband. So data-driven decisions, just to kind of define what we're talking about, I'm talking about a very general setting where we kind of have some data on covariates, treatments, and outcomes. So typically what you would do, you hope that, these are the treatments are assigned randomly or as if random, or if they're not assigned randomly, that it's unconfounded. So let's kind of just set away the typical causal inference kind of challenges. If you do have RCT or as if random data, then typically you can just build a predictive model that takes in the covariates and the treatments and predicts the outcomes. And then typically what we do with that is then we optimize a policy. So we try to figure out, okay, for these groups of people, they'll get these treatments. And then once you build that policy, once you've optimized it, you have to evaluate the policy so that you can say, we believe this policy will produce, an X% improvement compared to the baseline policy or whatever they're currently doing in practice. And so this is hopefully something that's strikes you as very common when it comes to targeting interventions to patients, discounts to consumers, assortments, whatever you want. And a big recent application I'm going to talk about is actually even matching refugees to cities. So this was a series of work actually by two independent teams that kind of ended up doing, at least at a high level, the same thing. So one paper was in Science from the Stanford Immigration Policy Lab, where they actually got data from both the US and Switzerland to try to predict, based on refugee characteristics, where they should be allocated. So, for example, maybe some people, maybe if you don't speak English, like you might survive better in a place that already has a strong community that speaks your language, compared to, some more rural area where that's more of a necessary skill. And so they actually built an algorithm, and they built a policy, and they show on their data that if you were to use the targeted refugee matching algorithm, you can do 40% to 75% better compared to doing random matching, which is typically what was going on. There was actually another team by Alex Hittelbaum, Nargis Ahani, and others that published a paper in OR where they had kind of more modest estimates, and they showed about 20% improvement and so on. So I just want to dig into this problem a little bit because I think it's illustrative. So the historical data is typically, again, X, T, and Y. X is your vector of refugee attributes, like how educated are you, did you speak English, and so on. T, the treatment here, is the placement location you're actually going to. And Y, because we're capitalists, is a 90-day employment outcome. We want to make sure that all these people become, tax-paying individuals in the country, right? So I'm not here to debate on the merits of that outcome. That's just what they use. So our goal is to learn a policy pie that takes these refugee level characteristics and maps people to locations in order to maximize the sum of 90-day employment outcomes. Unfortunately, budget constraints are hard, especially when you're doing refugee placement. So it's really a matter of swapping people around. So if I can figure out that, like, Ziv would do really well in New York and Hamsa should be in Philly, then that's kind of the match this kind of swap that I might make compared to a random policy. So they first train a predictive model, so kind of the classic estimate then optimize pipeline. So they train a predictive model, it's a GBM that predicts based on refugee characteristics and city locations how well they'll do in terms of 90-day employment outcomes. And then they optimize, so it's just like standard integer assignment problem. So you obtain a policy pi star that maximizes the sum total of all of the predicted outcomes, F. And then was subject to capacity constraints. And then now you have this tricky problem of how do you evaluate how well this policy is going to do. You don't have counterfactuals. So, if Ziv went to New York, I don't know how well he would have done in Philly, right? And so you might think, okay, well, I have this really nice predictive model that got good out of sample accuracy. I'm just going to go ahead and use that as an estimate for how well, any individual would do in their targeted location. And then you can compute the value of this policy. And this is how they get kind of the 20 to 75% improved employment. This is a very common kind of pipeline. The problem here is that this subjects you to something called a winner's curse because you trained a predictive model and it's almost tautological because the predictive, you obtain your policy by saying when the predictive model would think that you're doing well. So my model thinks Ziv will do really well in New York. Sorry to keep picking on you, Ziv, but you did introduce me. And therefore, now if I evaluate myself, again, based on the same predictive model, of course, the model said that you're going to do well in New York. That's why I put you in New York. And now I'm going to credit myself using the exact same kind of method. And so this is what we call the winner's curse. So let's say that on the x-axis, you have some trivial one-dimensional representation of your treatment and covariates, and on the y-axis, you have the outcome. Let's say this solid line is the true function f that predicts how well things will happen. And this, dashed line is kind of this noisy, unbiased model you've learned. Maybe it's a random forest or a GBM, so it's kind of less well-behaved and smooth. And so this green star here is like your best policy, your true best policy, and how well you expect to do. This red circle is what you might get if you maximize your estimated best policy. And the problem when you evaluate yourself, again, using your prediction, is that now I'm going to think I'm going to do exactly as well as this red circle tells me, whereas there's actually like a pretty large gap between how well I would have done and how well I actually did, right? And so this gap is kind of the winner's curse. Does that make sense? So we actually ran a realistic simulation where we just kind of, so this paper was really great and they reported kind of all their marginal probability distribution, sample sizes, and a lot of information. And so we built a simulator where we basically tried to mimic the exact characteristics of this data set, but we made it so that it was actually impossible to improve over random matching. So what we set it up to be is that refugee level characteristics are predictive of outcomes. So if you're educated and you speak English and you're young, you're going to be better off. And similarly, locations are predictive of improvement. So like if you get placed in a large city that has very good refugee integration support, then like you will do well. But there is no refugee location interaction. So there's no value to swapping two people around. The total amount, given the budget constraint is binding, the net amount of employment you're going to get is fixed. And so it's actually impossible to improve over a random policy. And so your ground truth effects are zero by construction. And if we apply the same pipeline, we get about a 60% improvement where none kind of exists. So the extent of this winner's curse problem is not small. It's not kind of a second order effect. I'm trying to argue that it's actually like very first order in these problem domains that we're interested in. So the green bars here, so the percentage change in employment is what we're interested in. We want a positive percentage change in employment. The green bars are using a model-free method, inverse propensity weighting. So old school statistics. And the pink bars are kind of what you get if you use a GBM model and follow the kind of model-based pipeline evaluation pipeline that I just mentioned. And like you said, like I said, it's like very confident that you can do really well again when there's actually like no effect size at all. So when we brought this up, there was like a bit of a question about what is the goal of policy evaluation. So I guess it would be good for us as a community to set a definition there. So we think that if you tell me a policy pi hat is going to be X% better than an existing baseline policy pi naught, it should indeed be approximately X% better with high probability. So some kind of pack style thing. So that it should have a low false positive rate, essentially. So if you tell me there's a good policy, this policy should be at least approximately good with high probability. So model-based evaluation does not satisfy that because if you use your model to evaluate your own predictive model to evaluate your policy, it's subject to winner's curse. And so it's almost definitely not gonna kind of hit that goal. So how would you evaluate? So like I mentioned, one of the ways that we tested was model-free evaluation. So this is inverse probability weighting, IPW, or augmented inverse probability weighting, or more generally, doubly robust methods, kind of go back all the way back to 1952 on a held out test set. This is sort of the gold standard as long as you have unconfoundedness and you have known propensities, which in this case is kind of additive random assignment, so it's easy. The problem is that nobody uses these methods as far as we can tell. So I'll show you a literature review shortly. But we surveyed about, over 50 papers in management science that recently were published in this area. Only two of them use model-free evaluation. And so like that's like what, 4%. So the problem is that these methods have huge variance, especially when you have high dimension or large action spaces. So most people end up using model-based evaluation, where you estimate the counterfactuals using your own estimated model, and then you evaluate your policy using exactly the same model that build to make predictions. Sorry. Or some people do something a bit more clever. There have been a couple variations that have been proposed where you learn not the exact same model, but a similar model, learn from a sample split or a bootstrap sample or something like that. Um, People have known for a long time, dating back to like, Harrison and March in 1984, but Smith and Winkler, they call it post-decision surprise or optimizers curves or winners curves. It's all kind of the same thing. That if you use the same predictive model F to evaluate yourself, that's not valid. We're going to show that actually a lot of these variations that people are using in the literature to sidestep that also does not make it valid. So if you really want a valid method, you need to use a model-free method. And I'll talk a little bit about how you might address this large variance issue.
So
Any,
sorry, a
yeah,
question. Can you clarify the difference
yes,
between
please.
this and overfitting and cross-validation?
Yes, sorry, I should have said that. So typically our like pipeline and prediction is to say, okay, let's evaluate the quality of our model in an out of sample test set. Right. So we'll look at mean squared error. And if we get, very low mean squared error, then we think, okay, we cross-validated this model and it like, isn't really overfitting, right? We have various checks to do that, right? That's not sufficient for avoiding the optimizer's curse specifically, because you can have very low mean squared error. For example, let's say most of your data is clustered in this region of the covariate space, then I actually have like a really good fit here. But then my optimization might pull an X that's sort of out of distribution. And then my error could be arbitrarily bad. And so it's the toolkit that we use to assess predictive accuracy isn't really the right toolkit for doing policy evaluation because of this kind of distribution shift. Does that answer your
Got
question?
it. Thank you. Yeah, got it. Thanks.
Thank you. I should probably have some slides on that, so thank you. Okay, so today I'll talk a little bit first about how common model-based evaluation is in our literature. Part of the reason we wrote this was so that we were getting a lot of papers to review that had this issue, and it was kind of challenging to explain. So we're writing this partly so that we can cite it and say, look at this. There are different justifications that are offered in the literature that people haven't necessarily looked at before, but we show that winner's curse can still persist and actually can be arbitrarily large even as our typical justifications are satisfied. And then I'll talk a little bit about how you can reduce. So like then we tell people, okay, do model-free evaluation, and then they always come back and say, I can't do model-free evaluation. The variance is too large. I don't have enough overlap between my policy and the existing policy. So then we actually look at the question of, can we train better policies? Forget the optimal policy. Can I train a policy that actually does have good overlap with the observational policy, so that I can kind of trade off, the average treatment effect and the z-score or the variance? So when we started this, we kind of did a sample of 55 management science papers from the last 10 years that do any kind of data-driven policy optimization or evaluation. This was really fun for me because my co-authors are LLM averse, so I got to use some of my LLM chops, which is very limited. So it turns out you actually cannot scrape the management science titles and abstracts off of their website because that's illegal. So you have to go to something called an EBSCO Business Complete database. So we ran a query for papers that basically are mentioning data, estimation, optimization, or policy in the title and abstract. So that pulls up in the last 10 years about 875 papers. There's probably a lot more papers that fit the bill, but they may not use these exact words in the title and abstract. And then that's a lot of papers. So we just fed the titles and abstracts to GPT 5.2 with like did some fine tuning and gave it a training set and all that to evaluate if this is an estimate then optimized paper. Like we're not looking for like, theory papers where the primary contribution is algorithmic. And we also want to make sure that in the abstract, they actually make a headline policy improvement claim. So it's not that like we develop a new method and then we calibrated it on real data, but rather we are actually saying, like the refugee paper, that we can improve refugee integration outcomes by, X%, right? So that brought the count down to 111 papers. At this point, we had to manually review them because there's only so much you can do. So we got the actual papers and the appendices in their supplement. It was a huge pain in the ass, mostly for Bryce. And manually reviewed, and this brought the number down to about 55 papers. And so that's the sample I'm going to be talking about. So these are 55 papers that are definitely doing some sort of estimate and optimize pipeline, and then are also making a headline claim that they're improving some application of interest by X% with their new policy. Out of these 55 papers, only 2 used valid model-free evaluation. 53 used invalid model-based evaluation. So again, these are published papers. So out of these 53, so the 2 are great. So I'm not going to talk about the 2 that were perfect. But out of the 53, 35, so the majority of them actually suffer from the traditional winner's curse, where we're not saying anything new, that they use optimization and evaluation use exactly the same predictive model. So this is the most pernicious form of the curse. But there's actually a decent chunk, like 33%, that are doing, some variation of this that kind of acknowledge the winner's curse and then say that they're doing some like clever variation of this. The typical justifications that they give for why this is an okay thing to do, I guess, related to your question, maybe Ali Reza, is that their predictive model is accurate on a held out test sample, that it's stable, so if they like perturb the training data a little bit, everything is kind of stable, that it's well calibrated. So, if it's a binary outcome, it kind of fits well. And that they used sample splitting. A very small number of papers use sample splitting for doing the policy evaluation. So they learned a separate predictive model on a test set. So it wasn't the same predict. So they use one predictive model to do optimization, and then they learn a completely new predictive model to do evaluation, which feels relatively good. Very few of them do kind of any kind of inference, so confidence intervals are typically not reported. And I think that's kind of the issue. We focus a lot in our field on the prediction and optimization part, and the evaluation part is a little bit of an afterthought. And the areas are kind of what you would expect for management science. There's a lot of revenue management, healthcare, and service papers that kind of fit this bill. The way in which we sample the papers is probably biased, so I'm not gonna claim this is the exact distribution. I'm just saying this is what we kind of found. So what are the justifications that are offered? So typically, first, like I said, that the model is really good. Second, that the treatments are randomly assigned, so they found an RCT data set, so you feel like, things should be good. The third justification is that you have a well-specified model. So let's say I really believe my choice model is multinomial logit, then maybe it's fine. And then lastly, that they might even do sample splitting. So this is actually at face value pretty reasonable sounding. Like let's say you have justification one and two or justification three. That implies that your estimated predictive counterfactuals are unbiased. So the model that you've learned is actually a very unbiased representation of the truth, right? And if you add in the fourth justification that your estimated policy improvement is actually independent from the policy you constructed because you trained your policy on one sample split and then you're evaluating your model from a different sample split, then you might think, everything is dandy and everything should be fine. We actually show that this is not the case. So this is where we kind of depart from the literature that even if we kind of give you all of this stuff, this still doesn't work. So the easiest picture that I can show you is in the case where the model is misspecified. It actually turns out that even if you have all four conditions, it still doesn't work. But I just like this because it's a very simple picture. So let's imagine that you have justifications one, two, and four, that you have a really good predictive model, assignment was random, and you did sample splitting. So here my treatment T is a number between 0 and 1. My outcome Y is, goes from 0 to Y max. And this solid line is my true function. And I'm fitting a misspecified function. So my solid line is actually some like piecewise linear function. The true function is actually this dashed function instead, which is just a linear function. So as you can see, the solid line reaches a max at t equals t naught. And whereas the fully linear function will just keep going up. And here, after t equals t naught, it drops to 0. So as I take t naught closer and closer to 1, this dashed line is going to be a much, much better approximation of the true model, given any kind of covariate distribution of t from 0 to 1, right? This misspecification is getting tinier and tinier and tinier. But the problem is that I'm taking a max, right? So that makes me interested in always, if I fit any kind of line with a positive slope, the t that maximizes this function is going to be t equals 1. And by construction, I've set it up so that that's going to be equal to 0 under the true function, right? So it's a little bit of a contrived setup, but you can see that there's like a big gap between the optimized policy and like getting good accuracy or good overlap on just your predictive function because of this distribution shift. So even if you have infinite data from an RCT, it's pretty trivial to see that as T naught goes to 1, your out of sample mean squared error goes to 0 because the dashed line really, really closely approximates the solid line, while the winner's curse kind of stays at a constant Y max, which is the largest possible winner's curse that you can get in this setting, and you can make it kind of arbitrarily large. And again, it's because the optimized decision is inducing a different distribution on your data set. And we think that this is actually not that unlikely in high dimensional problems because many data regions have very limited coverage. Like in the refugee simulation, there might be very few people from particular locations or very few people in certain cities or locations. And so you are kind of dealing with a small amount of data there. And so when you start taking maxes in those locations, you might kind of have very large winner's curse. The second issue, so if you take misspecification away, we can actually show that even without misspecification, this is still a problem as long as you have regularization. So if you fit your maximum likelihood estimator and you do sample splitting and n is large, this problem kind of goes away. But typically whenever we fit a non-parametric model, we know that it's, well specified. We need to regularize the model, right? If not, we don't have enough, like a random forest, we think will actually, eventually will be well specified with enough data and an expressive enough model class, but we need to regularize it. The problem with regularization is that it systematically biases your coefficients towards 0 in any low data directions. And in kind of any interesting problem, you have low data directions. And so even if you do sample splitting, we can show as n goes to infinity, that your estimated model can be arbitrarily accurate, like the last example, your out of sample mean squared error goes to zero. Your model can be very, very stable and still suffer arbitrarily large winners curse. I don't have a good picture for this one, but just to give you the kind of high level intuition, if you take like a simple linear model and I tell you that it's well specified, but I tell you that also the minimum eigenvalue of the covariance matrix is kind of not well defined. So there are two data directions that are highly correlated with each other. It's well known that you can fit ridge regression and you can get a very stable estimator and you can do really good in prediction error as well. But then you still cannot really distinguish between these two data directions. And so you can kind of show that you can still get arbitrarily large winners curves. So until you get to the point where the model is like perfectly fit and is no longer even without regularization, you kind of still have to deal with this issue. So I showed you guys this plot already on the refugee-based simulation. The OR paper actually mentioned the winner's curse. And so they actually offered stability as one of their arguments. They said, okay, so that's why we're not fitting a GBM model or any kind of high dimensional model because we see that it's not stable and it might be susceptible to winner's curse, but we can fit a lasso model. And they show that if you bootstrap the lasso model, it actually stays very stable. And so they have this more modest 20% effect size that they show is highly stable. But like I argued before, like theoretically, stability actually is not sufficient for you to avoid the winner's curse. And so in this ground truth zero simulation, we're still getting the same effect that, you know, there's a 0% effect and you can still get 20% effect sizes with a bootstrap lasso. And it gives you tight confidence bounds, but it's not kind of sufficient. Um, so maybe let me pause here. Are there any questions? Okay, cool. Sorry. I know I tend to talk fast. Okay, so whenever I talk about this, people are like, okay, so what should we be doing? And there's been a lot of recent interest in kind of debiasing or correcting for this winner's curse optimism. So my co-author Vishal at USC has written this paper using Stein's correction. He loves Stein. And other people have done, you know, bootstrap-based corrections. These are still model-based. So you're still using your model to kind of estimate what the bias might be. And so it kind of still is susceptible to some of these issues. Selective inference is another thing you can do, which is more limited in terms of the settings that you can address. If you really want to do model agnostic methods, you pretty much are stuck with AIPW or its cousins. Because that's the only way in which, because the only information that uses is the overlap between your policy and the existing policy. It does not use any kind of model-based information. And it's been kind of recognized, as I said, that like it has huge variance, and that's why people don't use it. And so there's been recent interest in kind of doing variance regularization on IPW. So we're going to be looking at that, and we're kind of going to be building off of that kind of direction. There's also been a lot of interest in aggregating treatments or units. So maybe I don't learn a personalized policy for every single individual to get one. Maybe I just cluster people into a few clusters. That kind of reduces the dimensionality of my problem. Similarly, if I have treatments, I can aggregate the treatments. Let's say I'm doing some kind of dosing problem. Instead of figuring out each person, should you get, you know, 0.35 milligrams or something, I can kind of bucket the treatments into kind of bigger buckets, again, to reduce the dimensionality of the problem. We are one of the first to write this down in terms of like explicitly doing downstream policy evaluation with statistical significance on a held out test set. So what does that mean? So we're imagining your typical researcher's pipeline whose goal is, you know, partly to publish their paper and say in their abstract that their policy improved things by X%. So they're gathering training and test data using some policy. They learn a targeting policy on the training data. And then if you want to do the kind of model-free method, your last step is to accept the policy only if it's statistically significantly better than the observational policy on a held out test data set using IPW or its cousins. I'm just going to talk about IPW for simplicity. Right? So the goal is to be able to say that, like, my policy does better with P less than 0.05 or something like that, right? You want to learn policies that actually can be deployed, or you can convince someone to actually deploy this policy by saying, I already did better looking at historical data. So I realized that I've gone this far through the talk and I have not defined inverse probability weighting or IPW. So let me take a minute to do that. So what does IPW do? And I'm really in love with IPW, I guess, because it is model free. So given a test set like XN, XT, and Y again, so your treatments here are from some observational policy. My Ys are the outcomes I'm interested in. My inverse probability weighting estimator for a policy's improvement pi is going to be basically just a reweighting of the observed outcomes. So for every outcome yn, I'm going to look at the probability with which I would have assigned this treatment divided by the probability with which the observational or whatever incumbent policy would have assigned this treatment. And then there's a -1 just to because we're estimating improvement, not the full effect size. Sorry, not the policy value itself, right? So what does this mean? If my policy happens to be equal to the observational policy, then this is just going to drop out and be 0 because obviously I can't improve anything. But if my policy is very different from the observational policy, so if let's say I have a deterministic policy, then my pi nt is going to be either 0 or 1. So every time I decide not to allocate something that the existing policy allocated something to, I don't get any information. And so that creates variance. Every time I allocate something to a policy and the observational policy is very unlikely to allocate to that person. Let's say I decide to send, Ziv to New York and there were like 50 different places that he could have randomly been assigned to. Now it's going to be like a 1/50, and then there's going to be high variance that kind of comes out of that. Right. And so this is an unbiased estimator in that I've made no assumptions. The predictive model doesn't show up here at all. It's just a reweighting of historical outcomes. But because of this pi nt over pi nt observational, the thing I've colored in red, this can have kind of very large variance if pi nt and pi nt observational are very different, which is annoying because if they're not very different, then you're not going to get much of an improvement, right? So there's like a tension here. So you can consider this optimization problem where my goal is to maximize the average treatment effect subject to a constraint that my z-score is above alpha, right? So this is the same as like this is the z-score we use for statistical testing. This is the same as me saying I only want this policy pi if it's statistically significant at this some p value, right? And as long as you're doing this on a held out test set and you're correcting for multiple hypothesis testing, this is not p-hacking. You're just trying to regularize the variance of the policy you're learning. Right. So this is equivalent, maybe unsurprisingly, as maximizing the average treatment effect subject to a constraint on the variance of the average treatment effect. And varying this beta over here actually gives you a Pareto frontier trading off the average treatment effect and the z-score. And that's what I'm going to kind of dig into in the next couple slides. So they say our contribution is really Bryce's contribution is to characterize the structure of this frontier. So I'll just focus on the 2-arm case because the K-arm case was kind of hard for me to follow, but it is in the paper. Okay, so variance regularization on its own does not do anything magical. At first, I was like, oh, maybe this would be amazing. But actually, if you think about the winner's curse, like, okay, so I had my point over here before. Now I regularize this function, and so maybe the circle jumps over here. And then if I regularize it more, maybe it jumps over here and there, and the max can kind of still jump all over the place. There's no stability in the class of policies that kind of trades out as you regularize the variance more and more. But it turns out that the solutions actually form a family of policies that are parametrized but just by the Lagrange multiplier of this variance constraint. And so that kind of gives some nice structure. So it turns out that the optimal policy for any level of constraint on the variance, pi and t star, is going to be, there's a clip here because the policy is a probability of allocating a treatment. So you want to make sure it's between 0 and 1, but you can kind of just ignore that. It's equal to the observational policy plus zeta times some amount. So what this means is that when zeta is equal to 0, my best policy is just the observational policy itself. I'm just going to give that back to you. That's a little bit of a degenerate solution that I'll talk about in a second. And then as I take zeta to infinity and I say, you know what, I just don't even care about this variance constraint anymore, I get back pi hat, which is typically what people are currently studying, which is just your a maximum average treatment effect. I don't think about variance. I just take kind of the optimal looking treatment for every individual. And you can show pretty trivially that as zeta increases, the average treatment effect decreases and the z-score decreases. So it looks a little bit like this. So on the x-axis, I have tau, which is the average treatment effect. And on the y-axis, I have the z-score, so like how statistically significant this policy is. So I start off with the observational policy itself at zeta equals 0. So this is this is very low variance, but it's not statistically significant because the effect size is 0. So what are you even trying to show, right? And then it turns out there's a little bit of a free lunch as you vary zeta, where tau doesn't change, but the z-score the z-score doesn't change, but tau steadily improves. So this is pi star zeta min. This is the most statistically significant policy that you can obtain given the data set that you have, as long as you're kind of using IPW. And so we don't know why it has this structure, but it does. And then after that, the policy, as you vary zeta, there's a strict trade-off. So you're going to lose more and more statistical significance in exchange for more and more of an average treatment effect until you kind of get this like pi hat, right? And like I said, most people are kind of looking at pi hat. We wanted to spend some time understanding pi star zeta min because that's probably actually something that's more credible or reliable that you can deploy, right? It's much more likely to have, well-behaved performance given the data set that you actually have to evaluate it. So it turns out that that this pi star zeta, like as you make zeta, some finite amount that's not infinity, it's basically just regularizing your optimal policy to be closer to the observational policy so that you have more overlap. So my intuition is always wrong in all these problems. So when we started, I was convinced that it would be something like, you would order all the units by signal to noise ratio or something, and there would be some cutoff. And basically, everyone above that signal to noise ratio would get a deterministic policy assignment, and everyone below that signal to noise ratio would get the observational policy, which sounds reasonable, right? Like if I know something is better for you, then I give it to you. If I don't know if something's better for you because you're too noisy, then I just give you the observational policy, and that way I don't get any variance. Of course, I was wrong. So it turns out that that is not how it goes. So let me show you. Actually, the most statistically significant policy looks like this. Everyone is random. So everyone, like no matter how big a signal to noise treatment effect, a signal to noise ratio you have, you are still random. You might be 99.9% likely to get arm one and only 0.01% likely to get arm two, but there's still no binding of a treatment to a unit except for one person. So basically, the moment that any individual binds to any arm with any determinism, now you start facing a strict trade-off in that you have to give up statistical significance in order to get a larger average treatment effect size. Um, and so just I guess the form of the IPW estimator, it's actually better for you to nudge more people away from the observational policy kind of smoothly rather than to actually bind anyone. Because once you bind someone, that particular data point has no value at all unless it happens to match the observational policy. So I thought that was kind of interesting. I find it fun when I'm wrong. So basically, most units should be receiving randomized treatment assignment, which is actually very different from how we deal with this problem right now in practice. So most people do some kind of dimension reduction, me too. So like we'll pool the treatments, we cluster individuals into small clusters, or we do some kind of regularization methods. And this would be very different, right? This would be that if I actually deploy the policy itself is random, which of course also has other downstream benefits because it will help me kind of collect more random variation in my data for future policy improvements. But not even thinking about that, this is just actually more likely to get you kind of the best performance for any given statistical significance level. So the most statistically significant policy, I guess This might be intuitive, but the average treatment effect ends up being like a sum of signal to noise ratios. And the z-score ends up being a kind of square root of signal to noise ratios, which kind of makes sense. So like if you have a bunch of units that have very clear signal, you're much more likely to be able to get something that actually improves over the incumbent policy. Let me pause here before I show some experiments. Any thoughts, questions?
Yeah, I have a question. So,
Hmm.
so, so it sounds like the first, can I just clarify? So basically, to find this sort of most statistically significant policy that you you can think of it as you smoothly increase data until one of your clips sort of fires, right? And then you stop.
Yeah.
So could you get into situations where you have like n is really large and okay, I'm going to say the word variance. I don't think I really mean statistical variance, but you have lots of, let's say, variability in sort of like how the different people are treated by the observational policy. And,
Hmm.
and you could imagine in this sort of situation that, one person is treated in such a way by the observational policy that your clip happens to fire like weirdly early on. Or like that if you added more people to your population, the sort of point at which one clip fires gets earlier and earlier. Is this like
Yeah, sorry, I totally forgot to mention this. So thank you for pointing this out. So in this in this simplification I'm showing, I'm assuming the observational policies in RCT. So
oh nice.
I'm assuming that they're doing like pi observational is half. But you're right. Like if the observational policy is something that's kind of not well distributed or not very random, then you would still be the structure I think would be similar, but it wouldn't be the same. Like you would be deterministic if the observational policy was deterministic as well. Yeah.
Okay, that makes lots of sense. Thanks.
Yeah. Thanks for pointing that out. Yeah. Other questions? Okay, so let me move ahead. So I am lucky enough to work in the same department as Katie Milkman and Angela Duckworth, who are very kind of famous behavioral scientists on behavioral change for good. And so one of the big things that they've been doing are these mega studies where you basically get like, I don't know, like hundreds of thousands of people, or I think now even millions of people, and you text them different nudges. And then they try to use that to kind of evaluate. So there's these large scale RCTs with like a ton of arms, but the signal to noise ratio is tiny, right? Like as you might imagine, if you are not getting a flu shot, a text message is not going to be the thing that changes your mind. But if you're on the margin, then it kind of helps you, right? So we're talking about effect sizes that are very small and very noisy. Which is kind of a good fit, but also just happened to be the data set that we had easy access to. And so the outcome we were looking at is, whether or not people vaccinate or not. The treatment is different kinds of text messages. Those are not the actual text messages. Those just Bryce going, flu is bad, get vax now. And the covariates are things like your age, your health conditions, zip code, past vaccinations, and so on. So in their mega study, they did not do any personalization. They just sent people randomly 22 different text messages. So the observational policy, the probabilities are like 1 over 22, right? So it's very noisy. And we're trying to understand, is there value to personalization, which is also a question that Anya Shetkina and Ron Berman recently explored with this data. We're specifically trying to do like this inference-aware policy optimization. So if you use the predictive model to look at the value of personalization, actually there are papers that have been published that look like this. Then you start seeing, wow, I can do, 20% better. I can get 20% people to vaccinate more. Sorry, I misspoke. The number of people who vaccinated more, you can do 20% better, which is a much smaller better number than 20% of the people. But still, huge effect size. But if you actually do, AIPW on a held out test set, you get much more modest numbers that are between 2 to 4%. So there is signal. It does look like you can do some sort of personalization, but it's hard. So these dots are different policies on our Pareto frontier, right? So this is the red dashed line here is basically 99% significance level, and the second one is 95% significance level. So you can see that if you take pi hat, it happens to just not be significant enough, and with an expected improvement of 3.5%. But you can also see that like even as I increase, even if as I increase my emphasis on this variance constraint, it's not until I get to this point where like I can really get some clear statistical signal that this personalization is actually helping. And you can get something. So this was what 3.5% for the best policy, which is not huge. But then this is 2% for something that's much more statistically significant and kind of reliable. Um, I told Katie this and she's like, 2%, 3.5%, like who cares about that? And I was like, fair enough. But definitely this is a case where I would argue if you are running with the optimal estimated policy, you're kind of better off doing this variance regularization because you don't lose too much effect size compared to the full one, but you get a lot more reliability. We can also look at how close these policies are to the observational policy. So the naive policy is just the average treatment effect maximizer. That gives you this 100% deterministic treatment assignment. This is the point that like maybe you might be most comfortable saying it's at least p less than 0.05. This actually overlaps with deterministic treatment assignment 46.6% of the time. So basically, less than half of people are saying, am I saying like, oh, Ziv, you're gonna get flu is bad or something like that. The text messages themselves are far more intelligent. Sorry, I just don't know what they are. And then at the 99% confidence level, nobody actually gets a deterministic treatment assignment. Of course, one person does, but that rounds down to zero. And so you actually end up giving randomized assignments to everyone, which when I talked to Katie, apparently is actually like easier to implement anyway. And so it kind of has these side benefits that you might also collect more data, but it's actually just a more stable, reliable policy to evaluate, um, to deploy. And again, overlap with the observational policy, again, we see it's monotonically increasing as you kind of go up. Um, we did the same thing for the refugee placement simulator that we built. But of course, this is a simulator, so we control kind of whether or not the ground truth effect actually has policy improvement potential. So like I mentioned, our original simulator, we had no interaction effects between refugee characteristics and locations. So it's impossible for anyone to do better. But then we tried adding kind of small interaction effects as well as medium interaction effects. So if you have small interaction effects, it's actually hard to outperform random assignment, but it's possible. If they're medium, then, then it starts getting easier and easier. If there's like a clear whopping, big thing, a big interaction effect that you can definitely see in the data, then of course you can use that to do better. And so again, this is kind of what the policy thinks it's doing, what the model itself thinks it's doing, and always thinks it's doing like, 25% better or something like that. But if you use AIPW in a held-out test set with no interaction effects, you can see it's not statistically significant if there's no effect. When you have small effects, you can see that you can start to actually find good policies if you do variance regularization, but the naive policy actually has a much smaller effect size and actually doesn't get any measure of statistical significance, very far from the statistical significance. Again, the model itself still thinks that it's doing fantastic. And then when you get to medium interaction effects, you see kind of what you might expect to see, which is that, the naive policy actually is like pretty reasonable. It's barely significant, and then we start having a trade-off, right? But with small interaction effects, because the data is so noisy, it actually isn't even the average treatment effect maximizing thing to do to take the max point estimate. That's the z-score that kind of holds when n is kind of larger. And so again, like this variance regularization might just have a lot of benefits if you just kind of have noisy data. Okay, so what was the point? Okay, so model-based evaluation are unfortunately widely used in our field, but they are invalid in the sense that they have a high false positive rate. So when you're doing policy learning, I think it's really important to kind of account for the downstream inference task. It's not that in every problem we care about statistical significance, but I think especially when we are thinking about writing papers whose goal is to kind of deploy a policy, especially in kind of high stakes settings, then it's important to kind of show evidence to decision makers or stakeholders that, this policy is improving. And it's important to do that in a model-free evaluation. One of the big things that was interesting for us is that and maybe this is obvious, but finding any policy is kind of much easier than finding the best policy, right? So I think in our field, there's a lot of focus on finding the best policy, but often random treatment assignment can actually get you much farther along than you might expect. I think this is interesting because with limited data, there might be a much richer kind of set of inference questions that we can ask. So we've only like recently started digging into this, but I'm going to spend like a slide on this, but you can actually, there's like a large number of policy learning problems, right? So I think a lot of the focus is on finding the best policy. And then the thing that I've been talking about in some variance regularization papers I've looked at is finding any policy that outperforms the observational policy, right? So I'm happy with the suboptimal policy as long as, I can show reliably that it does well. But there's actually a third question that I found really interesting, which is just an existence proof, right? Like, so a lot of times I work with a lot of medical folks. They've run some tiny pilot on their, 200-person continuous glucose monitoring problem or something. And they just want to know, looking at the data, is there any evidence that there's some kind of personalized effect, a personalized policy would do well here? Like, is it worth the money to like run a larger trial, right? Like, should I even bother collecting more data? Is there clear evidence for heterogeneous treatment effects? And, are they actionable, right? So actually 3 and 4 are also different. So sometimes you can find heterogeneous treatment effects, but that isn't sufficient to show that a personalized policy would actually do well, right? For example, like in the if all the heterogeneous treatment effects are, for example, positive and you don't have a budget constraint, then you might still give the treatment to everyone, right? And so we actually show sample complexity gaps between each pair of these problems. And so I think, if we don't have the data to answer 1 and 2, we can still answer 3, or maybe we can still answer 4. And I think there's kind of a richer class of problems here than maybe at least I was aware of. So again, I think there's lots of open problems here. Thinking about this for sequential settings or with model class selection or learning across kind of different RCTs. I would love to chat more if anyone has any thoughts or questions, but I'll stop here.
All right. Thank you. Let's give Hamsa a virtual round of applause for a wonderful talk, and we have some time for questions. Okay, well, I have some questions to I have one question to kick things off, which is a little bit related to what I was to my last question. So I guess the
Mhm.
succinct version of my last question was, what can you say? What can you say if pi observation isn't a randomized control policy? Um, and
Oh, if it's a deterministic policy.
or just even less uniformly random. And now with the context of the latter of your comments at the end, you could ask,
Yeah.
if like straight uh jumping immediately to the best policy, right, is,
Yeah.
one thing you can try to do. But I like this sort of question of, can you improve the policy? And basically, if you can
Hmm.
improve over non-uniform policies, that at least provides a path towards gradual improvement, maybe going towards an optimal or at least locally optimal policy. So is that something that's like feasible,
Right.
or would this completely break once things get non-uniform enough?
No, this is a great question. So non-uniform is fine. I mean, technically this optimization formulation is fine no matter what you do, but the
Sure.
problem is that the variance is going to be, so if pi and t observational is deterministic, like let's forget the uneven case, then there's nothing you can do, right? Because basically whenever pi and t is not equal to pi and t observational, there's no overlap. And so I have no counterfactual. And so I only have counterfactuals when we're exactly equal, when my exact improvement is 0, right? So it's like clearly impossible when the observational policy is deterministic. If it's highly non-uniform, that's actually fine as long as you believe that there's still no unobserved confounding. It might just be that you can only learn improvements in directions where you have improvements, right? So imagine that like for one cluster of people, I'm fully deterministic, then I have to be fully deterministic and
Hmm.
match the observational policy on those people. I can only learn improvements for the people that kind of got a variation in the policy improvement. Does that make sense?
Yeah. Okay. Thanks.
Yeah. Sorry that you had to fill in the gap.
No, no, no. Cool. Any further questions?
Well, yeah, thanks, Hamza. That was really fun.
Hi, Shane.
I think, hey, you've scared the willies out of me now. Like
Oh no.
what, now that I'm sort of thinking about this, what can I learn? And, like the conversation you just had with Zeev, I think helps to understand that. Basically, wherever there's kind of sufficient randomization, that's a place where you can explore. But where you don't have that, you should steer clear. Are there other takeaways like that?
Yeah, I think there are a couple things that in the like CS literature they do. For example, I think this kind of matches the whole original winner's curse discussion that you can't go off distribution. So you can only learn in places where you already have enough variation because then you have good, overlap. And you don't want to learn policies that are very far from the data you've seen because then it's very likely that, you're making inferences in places you shouldn't be making inferences in. So the couple famous examples are the sepsis treatment using reinforcement learning. They basically found that I think for really risky people, you shouldn't treat them at all because there were like two people that had some unobserved, data going on in the background or, had some special condition and got treatment. Anyway, so like it's off distribution essentially. So I think a couple simpler things that you can do are just to like have some sort of KL divergence constraint to say that your policy is similar. Or you can try to like learn this bias correction. The problem with learning the bias correction experimentally that we've found is that if you can't estimate the mean well, you often can't estimate the variance well either. And so when you optimize, you're always going for the outlier, right? And so
Mhm.
we tried, maximizing the lower confidence bound, for example. So instead of maximizing mu, I maximize mu minus sigma. And hopefully that's like you maximize the pessimistic estimate, right? But if you have a very bad estimate of sigma in some portions of your distributional space, then you again kind of run into the same problem, which just made me, after looking at a lot of the recent literature, I was like, man, this Rubin guy really had it right all along.
No, thank you. That's helpful. And then just a quick follow-up, if I may.
Yeah.
The people that are coming from the robust optimization community, um, my takeaway is that they're they're guilty in some similar ways if their uncertainty sets aren't sort of properly calibrated. But do you have anything to say in that realm?
Yeah, so I don't have anything. So I just gave this talk recently, and Alex Jaquillo is there, and he pointed me to this like DRO literature, which I know very little about, I will confess. Um, but I think Dan Kuhn's stuff has said something about this post-decision surprise that DRO can be optimal to minimize post-decision surprise. I have to still kind of read the paper and dig in. It's still model-based though, so you're still kind
Yeah.
of hoping that you specified everything correctly. I do a lot of this machine learning work, right? So like a lot of this stuff, like they're fitting random forests, neural nets, at which point I don't believe the model at all. And it's, very likely to overfit in kind of sparse data regions, and that's known, and we accept that because you get low average mean squared error on the test set. But again, wrong distribution if you're optimizing. So I think if you're using these machine learning methods, it's really important, or these very high dimensional, like if you're fitting a high dimensional MDP or a structural model or something like that, I think then it's important to use model-free evaluation. But if you're fitting like a very simple OLS or MNL model or something like that, where maybe you can even visually check that you have good overlap, then I think these model-based methods might help a lot. And you probably can specify the uncertainty sets well, but something I'm hoping to dig into more. So thanks for bringing it up.
Yeah, no problem. Thanks for the pointers. One last thought, if I may. Warren Powell did a lot of work with trucking companies, and
Mhm.
I may be misrepresenting what he told us in a plenary at some point, but what I remember was that he was telling us about something he called the happiness function. And the happiness function is you want to introduce a different policy for how you dispatch loads to drivers. But if you are too different from what they've done in the past, then you don't have the credibility to sort of go ahead. Plus, maybe your model's wrong, right? So you're just recommending crazy stuff. So he had this thing he called the happiness factor, which was in some sense, it was kind of like a knob you could turn from 0 to 1. And when it was set to 0, you basically did what they were doing right now. And then as you moved away from 1, you would slowly move towards your dispatch decisions. And what I thought I saw basically shadows of that in what you were presenting. Does it sound like, I apologize for the butchering of the description, but does this look a little bit like some of the stuff you're doing?
I think if you're doing online learning, you can get away. I'm not sure if he was doing online learning just based on his work, I would guess.
Probably not. No.
Uh, it wasn't online learning, it was like a one-time. Because this really applies if you're doing like a one-time decision, right? Like for the refugee integration, like you're deciding that the government is instead going to run this other policy. A lot of things in healthcare, you don't if you are continuously collecting data, there's some chance that you might actually go back. As long as you have enough randomization, you'll go back and correct the mistakes that you made, right? So I go off distribution, I see the models misspecified and I was totally wrong, and I kind of might move back as long as you're doing it intelligently. Um, Without reading it, I wouldn't know, but
Yeah, no, no,
yeah,
no problem. I mean, it's
sorry.
really more of a practical heuristic, but um,
Yeah.
but yeah, I think the way he was implementing it was kind of through a series of stages of these things. So he would come up with something, he would try setting the happiness factor to like, 0.1 or something, and then he would run for a while, like a month, and then he would sort of see how it's going, and make some adjustments, dot, dot, dot,
I
continue
love the
maybe.
name happiness factor. I mean, I should put that in my work too.
It was, Warren had some real impact with
That's awesome.
these freight companies, and he had some good things to say.
Yeah, I'll look it up. Thank you.
Yeah, no, thank you. By the way, is this work? I sort of missed it. Do you have the paper on this?
There's two papers I talked about. One is the meta survey kind of thing, and then the other one is the inference-aware policy optimization. Both are on archive and on our websites.
Thank you.
All right. Well, let's thank Hamsa one more time. And then if people have lingering questions, I can leave the Zoom room open. Snap continues next week with a talk by Alan Charlerwolf, and then one more, and then that'll be the second to last talk. We have one more talk at the start of June by Benjamin Van Roy. So hope to see you there. Okay, thanks again, Hamsa.
Thanks so much, Sid.